Hello and welcome. Settle in, get comfortable, and prepare to drift off to the sounds of the cosmos. Imagine waking up one morning to find the world outside your window is half as bright as it used to be. The sun is noticeably dimmer, street lights look distant and weak, and the light bulb in your own room barely flickers. Sounds like the start of a sci-fi novel, doesn't it? But what if I told you that something similar, only on a truly colossal scale, is happening right now to our entire universe? Astronomers worldwide have encountered a mystery that challenges our fundamental understanding of the cosmos. Data collected over the last few years points to an astonishing fact. The universe is dimming and it's fading far faster than any of our current models predicted. This isn't just the slow, predictable dying of distant stars. This is a global, unexplained darkening, as if someone is slowly turning the dimmer switch on all of creation, lowering the overall illumination of existence itself. In tonight's sleep lecture, we will journey into the heart of this enigma. We won't rush. We will slowly and calmly explore how scientists arrived at this shocking conclusion, what hypotheses they are proposing, and what this might mean for us all. Prepare to immerse yourself in one of the greatest mysteries of the 21st century. Before we delve deeper into this encroaching darkness, let's first establish, how do you even measure the brightness of an entire universe? It's certainly not a light bulb you can simply hook up to a voltmeter. The answer lies in painstaking, years-long labor. Astronomers rely on what is called the extragalactic background light, or EBL. Imagine you are in a completely dark room with no direct light source whatsoever. If there are lamps burning in the neighboring rooms, their light will leak under the door, reflect off the walls, and the room won't be absolutely black. You will perceive a faint, diffused glow. The extragalactic background light is exactly that, but on a cosmic scale. It is the cumulative light from every star and galaxy that has ever existed in the universe. It permeates all of space. To measure it, scientists point powerful telescopes like the Hubble Space Telescope toward the seemingly most empty patches of sky. They spend hours, sometimes days, gathering photons arriving from these incredibly dark regions. By analyzing this light, they can map the cosmos's overall luminosity. For decades, this value was considered relatively constant, factoring in only the slow, predictable decline as stars age. We had an elegant, beautiful model describing how the universe was born in the blinding flash of the Big Bang, and then gradually cooled, igniting billions upon billions of suns. But new data shattered that peaceful idyll. It turns out the drop in brightness is neither linear nor smooth. There was an unexpected, dramatic shift. The universe has dimmed almost twofold compared to what we observed just a few thousand years ago, a blink of an eye by cosmic standards. But where did this story begin? The first real alarm bells started ringing during the analysis of data from the Galaxy and Mass Assembly Project, or GAMA for short. GAMA is one of the most ambitious sky surveys ever undertaken, examining hundreds of thousands of galaxies at vastly different distances. The project's main goal was to create a precise 3D map, showing how matter is distributed across the universe. But alongside that, scientists were also meticulously measuring the light that these galaxies emit. When the international team of astrophysicists compiled all the data, covering light from the ultraviolet to the far infrared spectrum, they were in for a shock. They discovered that the portion of the universe they studied is producing only half the energy it did just 2 billion years ago. Imagine a major city suddenly cutting its power consumption by half in a relatively short period. Your first instinct would be to check the meters. And that's exactly what the researchers did. They recalibrated their instruments, factored in every possible margin of error, and completely reviewed their calculation methods. But the result was undeniable. The universe is genuinely fading out. The light we receive from distant galaxies has traveled for billions of years, meaning that when we look at them, we are effectively looking into the past. By comparing the light of these older, more distant galaxies with that of the younger, closer ones, astronomers managed to plot the universe's energy output over time. And that graph revealed not just a slow decline, but a dramatic crash. This discovery, once published in prestigious scientific journals, initially met with serious skepticism. Many experts suspected it was merely a localized anomaly or some unknown factor they hadn't accounted for. However, subsequent observations made using a host of other instruments, including space observatories run by NASA and the European Space Agency, only confirmed the initial findings. The universe is indeed undergoing a phase of dramatic energy decline. It is slowly but certainly plunging into twilight. Now, this doesn't mean the sun is going to wink out tomorrow. We're talking about the average production rate across the entire cosmos. But the sheer fact that this process is happening forced scientists to search for the underlying cause, and that's where things got really interesting. The first and most obvious hypothesis the scientists considered was, as they say, right on the surface. What if something was actually preventing that light from reaching us? What if the space between galaxies had simply accumulated more dust? We're used to thinking of space as a perfect, absolute vacuum, but that's not entirely accurate. The intergalactic medium is filled with highly rarefied gas, elementary particles, and, yes, cosmic dust. This dust is made up of tiny particles of silicates and graphite expelled into space either by supernova explosions or carried by stellar winds from aging red giants. Every single speck of this dust is a microscopic obstacle. On its own, it's virtually invisible, but when a photon encounters trillions of these specks on its journey, the cumulative effect becomes significant. The light is absorbed and scattered, making distant objects appear both dimmer and redder. This phenomenon is known as interstellar reddening. The core hypothesis was that, for some unknown reason, the amount of this intergalactic dust had sharply increased. Perhaps there had been some global cataclysm, say, a massive series of ancient supernova explosions that had literally smoked up the cosmos. Or perhaps the properties of the dust itself had changed, making it much more efficient at absorbing light. This idea was attractive, specifically because of its simplicity. It didn't require tearing up the fundamental laws of physics. It simply suggested that we had underestimated how polluted the universe really was. To test this hypothesis, astronomers began searching for clear evidence of this hypothesized reddening effect. If dust was the culprit, it should absorb blue light much more effectively than red light. This meant the light spectra of distant galaxies should show a systematic shift toward the red end, a shift stronger than the one already explained by standard cosmological expansion. Careful measurements followed. Scientists compared the colors of thousands of galaxies, specifically those located at similar distances but observed in vastly different directions. If a single, uniform cloud of dust were causing the dimming, it should affect all galaxies equally, regardless of direction. But the results proved contradictory. While the reddening effect was indeed observed in some directions, it was completely absent in others. The pattern simply didn't hold up. Dust, therefore, could not serve as the universal explanation. While the cosmic dust hypothesis couldn't fully explain the observed dimming, it pushed researchers toward a deeper analysis. What if the issue isn't that light is being blocked, but that less light is being created in the first place? This led directly to the second major theory, a slowdown in the rate of star formation. The universe is not static. Stars are constantly being born and dying. New stars form from gigantic clouds of gas and dust, collapsing under the pull of their own gravity. At the center of such a cloud, temperature and pressure rise until thermonuclear fusion begins and a new sun ignites in the sky. This process was especially vigorous in the young universe, peaking roughly 3 to 4 billion years after the Big Bang. Back then, galaxies were filled with gas, and stars popped up like mushrooms after the rain. Astronomers call this highly active era the cosmic noon. Over time, however, the supply of this building material, free gas, began to dwindle. The gas was either used up to form stars or violently expelled from galaxies by powerful supernova explosions. As a result, the overall rate of star formation started to gradually decline. This is a well-known and long-predicted process. Our own galaxy, the Milky Way, passed its peak star-forming activity long ago. According to standard models, the universe should be dimming slowly and smoothly, as old stars burn out and new ones are born less and less frequently. But what if this process hasn't gone according to plan? What if, for some reason, star formation has slowed down much more abruptly than we ever predicted? Perhaps some unknown mechanism is actively suppressing the birth of new stars in modern galaxies. Take, for example, the supermassive black holes at the centers of galaxies. When they actively consume surrounding matter, they eject powerful jets of energy, which heat and accelerate the surrounding gas, preventing it from collapsing to form stars. It's possible that the recent activity of these black holes has been severely underestimated. They could be literally sterilizing their galaxies, halting the birth of new generations of suns. This shift can be illustrated by comparing two types of galaxies: a vibrant spiral galaxy filled with young blue stars versus an older elliptical galaxy composed mainly of old red stars. The observed darkening might signal that the universe is making a massive collective transition from the first state to the second. The idea of a sharp drop-off in star formation seems plausible, but it definitely has its weak points. The main question is, why did this decline happen so suddenly and so synchronously across the vast expanse of the observable cosmos? Galaxies are isolated systems, essentially living their own separate lives. It's hard to imagine a single process that could force them all to simultaneously turn off their stellar nurseries. That would be like children suddenly stopping being born in every city across the globe on the same day. Such a synchronized effect demands some kind of global, all-encompassing factor. And this is where we enter the domain of modern physics' greatest enigma, the realm of dark energy. Dark energy is the hypothetical form of energy believed to be responsible for the accelerated expansion of the universe. We don't know what it is, but we certainly see its effects. It acts like anti-gravity, pushing galaxies apart at an ever-increasing pace. According to the standard cosmological model, the density of dark energy in the universe is constant. It does not change over time. This property is described by the so-called cosmological constant, which Albert Einstein once introduced into his equations and then famously discarded. But what if he was wrong? What if dark energy isn't a constant? What if its power changes over time? There are theoretical models suggesting that dark energy might actually intensify. One such model describes what is called phantom energy. If its density increases, the acceleration of the universe's expansion wouldn't just continue. It would accelerate catastrophically, growing exponentially. Eventually, perhaps tens of billions of years from now, the power of dark energy would become so overwhelming that it could tear apart the gravitational bonds within galaxies, star systems, and even rip the atoms themselves to shreds. This terrifying scenario is known as the Big Rip, but less dramatic events might precede this apocalyptic finale. The strengthening of dark energy could directly impact the rate of star formation. The expanding space would stretch out gas clouds, preventing them from reaching the critical density necessary for gravitational collapse and the birth of new stars. If dark energy recently transitioned into a more active phase, it could be the global off switch that synchronously dimmed star formation across the universe. The overall cosmic dimming we observe might in fact be the first warning sign of the coming Big Rip. This hypothesis is certainly both captivating and frightening. It transforms a simple astronomical observation into a potential prediction for the end of everything. While it remains only a theory for now, it forces us to fundamentally rethink the forces that govern our world. As we continue to explore the most profound mysteries of cosmology, we can't ignore the other great dark player on the cosmic stage: dark matter. If dark energy pushes the universe apart, dark matter, conversely, is what holds it together. It is an invisible substance that neither emits nor absorbs light, yet possesses gravity. We know it exists because we observe its gravitational influence on the movement of stars within galaxies and on entire galaxy clusters. Without dark matter, galaxies would simply fly apart, as the visible matter they contain isn't enough to keep stars in stable orbits. Dark matter accounts for about 27% of the total mass energy of the universe, roughly 5 times more than the ordinary baryonic matter that makes up you and me. Just like dark energy, we know almost nothing about the true nature of dark matter. We currently hypothesize that it consists of exotic, yet-to-be-discovered elementary particles. The standard model often assumes dark matter is stable, that it doesn't decay and interacts with nothing except gravity. But what if even that assumption is wrong? Alternative theories suggest that dark matter particles might be unstable. They could slowly decay, transforming into other, lighter particles, such as neutrinos or even photons. If this decay were happening, it would necessarily release energy. It seems logical that this should make the universe brighter, not darker. However, there are other scenarios. For example, dark matter might not decay, but instead annihilate when particles collide with each other. Or it might interact with ordinary matter in ways we simply cannot predict yet. Let's imagine a hypothetical model where dark matter transitions into a new state that allows it to absorb light. Or perhaps its decay creates particles that act as a catalyst, accelerating the transformation of interstellar gas into the very cosmic dust that dims the light of stars. The link between the universe's dimming and the properties of dark matter is currently purely speculative. We have no direct evidence supporting such a hypothesis. Nevertheless, it opens up an entirely new avenue for research. Proving that the properties of dark matter change over time would be a revolution in physics, and the observed fading of the cosmos might be the first observational evidence of that change. Scientists are actively searching for indirect signs of dark matter decay, such as an excess of gamma rays or positrons coming from the center of our galaxy, where dark matter density is expected to be highest. For now, the results remain ambiguous, but the search continues. When conventional explanations fail, the boldest minds are forced to confront the most fundamental questions. What if the issue isn't with the universe itself, but with how we interpret its laws? What if this dimming isn't a genuine physical process, but rather an illusion stemming from incorrect foundational assumptions about physics? This is the most radical and difficult path to verify. It demands a complete overhaul of the bedrock upon which modern cosmology is built. One such foundation is Einstein's general theory of relativity, which describes gravity. The other is the standard model of particle physics. We tend to view these theories as immutable truths, yet the history of science shows that every theory has its limitations. Perhaps at the vast cosmological scales we are observing, the laws of nature function subtly differently. Consider the old, long-discarded hypothesis of tired light. In the early 20th century, when the redshift of galaxies was first observed, scientists like Fritz Zwicky proposed that it wasn't due to the universe expanding, but rather that photons simply lost energy traveling across vast distances, essentially suffering from cosmological fatigue. This idea was later refuted by observations because it failed to account for numerous other cosmological effects, such as the consistent brightness of Type Ia supernovae. But what if there is some yet undiscovered mechanism governing how light interacts with space-time itself? What if the vacuum of space isn't truly empty, and after traveling for billions of years, light actually loses a fraction of its energy, perhaps converting it into gravitational waves or other fundamental particles? If such an effect exists and its intensity has recently increased, it could easily create the illusion that distant galaxies are growing dimmer. Another possible avenue involves modifying the theory of gravity itself. There are already several compelling alternatives such as MOND or modified Newtonian dynamics, or theories that incorporate extraspatial dimensions. In some of these models, the gravitational constant might fluctuate over time or vary based on the density of matter. Such a fundamental change would directly impact the dynamics of cosmic expansion and consequently alter our perception of the brightness of distant objects. Naturally, any new theoretical framework must not only account for the universe's dimming, but also remain consistent with all existing astronomical observations, from the orbital mechanics of our solar system to the cosmic microwave background radiation. This is an extraordinarily difficult challenge. However, the sheer possibility that we stand on the threshold of uncovering entirely new physics is inspiring a whole generation of theorists. The mystery of the dimming cosmos might well be the key that unlocks the next great scientific revolution. To find answers to this fundamental cosmic mystery, astronomers are placing enormous hope in their new flagship instrument, the James Webb Space Telescope. Launched at the end of 2021, Webb is Hubble's successor, but with vastly superior capabilities, especially in the infrared spectrum. Why is this crucial to solving our problem? First, Webb can look much further back into the universe's past. Its massive mirror and ultra-sensitive detectors allow it to capture light from the very first galaxies, which formed only a few 100 million years after the Big Bang. This allows us to trace the history of star formation virtually from its beginning right up to the present day. By comparing Webb's data on the early universe with information from Hubble and other telescopes covering later epochs, we can construct an incredibly precise and detailed curve of energy production over time. We will be able to see whether the drop in cosmic brightness was a sudden jump or a more gradual process that began long ago. We can pinpoint the exact moment in cosmic history when this crucial turning point occurred. Secondly, Webb is perfectly suited for studying that crucial cosmic dust. Infrared light passes through dust clouds much more easily than visible light. By observing galaxies in the infrared, Webb can effectively see right through these dusty veils, allowing it to measure the true, not just the apparent, rate of star formation inside them. Furthermore, the dust itself absorbs starlight, heats up, and begins radiating in the far infrared. Webb can capture this thermal emission, allowing scientists to directly measure the amount of dust in distant galaxies. This will finally help us confirm or refute the hypothesis that the universe is becoming heavily dust-obscured. And thirdly, Webb possesses unprecedented spectroscopic capabilities. It can split the light from distant objects into a spectrum with extremely high resolution. This allows for precise measurement of the gas's chemical composition, its velocity, and the physical conditions within star-forming regions. This data is key to understanding the exact mechanism that suppresses the birth of new stars, whether it's the activity of black holes or some other factor. Webb's initial findings have already delivered many surprises, showing that early galaxies were more massive and developed than theoretical models predicted. It is highly likely that in the coming years, this telescope will be the one to finally give us the answer to why the universe is getting darker. Science isn't a monolithic truth, it's a vibrant, bubbling process fueled by fierce debate and discussion. The mystery of the universe's dimming is certainly no exception. The scientific community is sharply divided on the root causes of this phenomenon, with various research groups fiercely championing their own hypotheses and constantly bringing forward new evidence. Proponents of the star formation decline theory point to observational data from specific galaxies. This data reveals that in many systems, particularly massive elliptical galaxies, the process of forming new stars has virtually ceased. They argue this represents a natural aging of the universe, one that might simply be accelerating faster than we anticipated. Their opponents, advocates of the cosmic dust hypothesis, counter that we cannot judge the entire cosmos based on a handful of examples. They highlight that many galaxies actively engaged in star formation are hidden from our view by dense, obscuring clouds of dust. In their view, we are simply missing a significant portion of the universe's youthful light. If we could account for this obscured luminosity, they argue, the apparent sharp decline might vanish entirely. The debate gets even sharper when we bring in dark energy and dark matter. Theoretical physicists developing exotic models see this cosmic puzzle as a potential opportunity to validate their boldest ideas. They construct intricate mathematical frameworks linking the universe's fading light to shifts in fundamental constants or the existence of new fields and particles. Observational astronomers, however, approach such theories with considerable caution. They demand much stronger evidence, often pointing out that many of these models are too flexible, so adaptable that they can be tuned to explain virtually anything. There is also a camp of skeptics who believe the entire problem might be rooted in systematic errors in observation or interpretation. They remind us that measuring extragalactic background light is an incredibly complex task. We must filter out light from stars within our own galaxy, zodiacal light, which is sunlight reflected by dust in the solar system, and a host of other interferences. A slight miscalculation in accounting for just one of these factors could easily lead to a spurious result. This scientific disagreement is not a sign of weakness, quite the opposite. It is the signature strength of the scientific method itself. New knowledge is born precisely in the collision of different viewpoints and through relentless mutual verification. Every hypothesis is tested rigorously and every detail is scrutinized under a microscope. Whatever the final answer turns out to be, it will be forged in the crucible of this intense intellectual struggle. Let's take a moment away from the formulas and the graphs to consider what this discovery truly means for us on a deeper philosophical level. The realization that the universe, our vast home, is slowly fading away inevitably stirs up a complex mix of emotions. On one hand, this knowledge is deeply humbling. It reminds us of the fleeting nature of our existence when measured against cosmic timescales. The era of bright, burning stars, the very epoch that made life on Earth possible, is merely a brief flash in the universe's long history. We are living in a privileged moment, a cosmic spring, but it will inevitably be followed by a long, cold, and dark cosmic winter. This thought can feel crushing. Everything we create, all our achievements, the entire history of humanity, will ultimately dissolve into the cold darkness of a dying universe. But conversely, this same knowledge can fill us with awe and a profound sense of responsibility. We are the children of the stars, born from the ashes of their demise, and we have been granted a unique opportunity to be witnesses to this grandiose cosmic drama. We are the part of the universe that is capable of realizing and contemplating its own fate. This places a distinct obligation upon us to study, to understand, and to cherish the world we inhabit. Perhaps we are the only audience for this cosmic spectacle, and our duty is not to look away but to observe it clearly, even if the final act promises to be a sad one. Moreover, this mystery once again underscores just how little we truly know. We are accustomed to taking pride in our scientific achievements, our telescopes that can peer 13 billion light-years into the past. Yet, a seemingly simple observation that the light is dimming baffles the best minds on the planet. The universe remains vast and full of secrets, and beyond every horizon we manage to cross, even more astonishing puzzles await us. And perhaps the core meaning of our existence lies in this perpetual striving for knowledge, this endless journey from ignorance to understanding. The universe may be growing darker, but the light of the human mind seeking to comprehend it continues to burn brightly. What if what we are witnessing isn't a one-way path toward final decay, but merely one phase of a gigantic cosmic cycle? The idea of a cyclical universe is as old as time itself. Many ancient cultures and philosophical systems held the belief that the cosmos doesn't just move linearly from point A to point B, but rather progresses through repetitive cycles of birth, death, and rebirth. Modern cosmology largely adheres to a linear model. The Big Bang, expansion, followed either by eternal cooling, often referred to as heat death, or a collapse back into a singularity, the Big Crunch. However, cyclic models do exist, attempting to reconcile modern scientific findings with this ancient intuition. One of the most prominent is the ekpyrotic, or cyclic, universe theory developed by Paul Steinhardt and Neil Turok. In this theory, our three-dimensional universe is described as a brane, essentially a membrane floating in a higher dimensional space. Periodically, our brane collides with a parallel brane. Each collision triggers a new Big Bang, initiating a fresh cycle of evolution. Under this model, the universe's expansion is eventually followed by a slow contraction, not all the way back to a singularity, but only until the moment of the next collision. How might this relate to the dimming we observe? Perhaps we are currently in the phase of the cycle where the dominance of dark energy which drives accelerated expansion is nearing its end. Its effect might be weakening, gradually giving way to the gravitational forces that will slowly begin to draw the universe back together. Such a shift in the balance of forces could suppress star formation and lead to an overall reduction in luminosity. This means the dimming isn't a sign of final death, but merely a precursor to a coming cosmic exhale before the next great cosmic inhale. Another variant of the cyclic model proposes that fundamental physical constants, such as the speed of light or the gravitational constant, might slowly change over the course of a single cycle. The fading we observe could be a consequence of such a shift, which would then be reversed during a later phase of the cycle. For now, these ideas remain on the periphery of mainstream scientific thought. They are extremely difficult to test and require the existence of exotic concepts like extra dimensions and brains. However, they certainly give us food for thought and serve as a reminder that our future may not be as predictable and definitive as it currently seems. Perhaps the darkness we are observing isn't the end, but merely the calm before a brand new dawn. While theoreticians continue to refine their models, observational astronomers press on with their painstaking work, gathering crucial evidence. To solve the mystery of the universe's fading light, simply documenting the phenomenon isn't enough. Scientists must find other, independent pieces of evidence that point clearly to one specific cause or another. A genuine scientific hunt for clues is now underway. One key area of research is examining the distribution and properties of intergalactic gas. If the hypothesis that star formation is being suppressed holds true, we should observe corresponding changes in this gas. It should become hotter and more tenuous, having been agitated or whipped up by energetic processes like black hole jets. Astronomers investigate this by analyzing the spectra of distant quasars. As a quasar's light travels toward Earth, passing through vast clouds of intergalactic gas, it leaves fingerprints in the spectrum, absorption lines. These lines allow scientists to determine the temperature, density, and chemical composition of the gas at various epochs throughout the universe's history. By comparing these cosmic chronicles, researchers are attempting to understand exactly how the conditions for stellar birth have changed over time. Another crucial clue might be hidden in the cosmic microwave background, the echo of the Big Bang. This radiation permeates the entire cosmos and carries information about the universe's state when it was only about 380,000 years old. If any global energetic processes occurred in the recent past, such as the massive decay of dark matter or a significant change in the properties of dark energy, these should have left faint traces or distortions in the CMB map. Spacecraft like the Planck satellite have created incredibly detailed maps of this radiation, and scientists are now combing through them, searching for anomalies that might correlate with the observed cosmic dimming. A further avenue involves the search for so-called standard candles at extremely great distances. Standard candles are astronomical objects whose intrinsic luminosity is precisely known. The most famous among them are type Ia supernovae. By accurately measuring their apparent brightness, we can precisely determine their distance. It was, in fact, the use of these supernovae that led to the discovery of the accelerating expansion of the universe. If we can find and measure a sufficient number of these supernovae in very distant galaxies, we can construct an ultra-precise map of the universe's expansion and definitively test whether the density of dark energy has changed over time. This work requires immense effort and the global coordination of many observatories, but it is precisely this effort that could provide the decisive piece of evidence in this cosmic case. Let's revisit the hypothesis concerning the decline in star formation rates and take a closer look at the details. We've already touched upon the idea that the gas reservoirs within galaxies are being depleted, but that's only one side of the coin. The other, equally crucial factor is the efficiency with which that gas is actually converted into stars. It turns out that having plenty of gas in a galaxy doesn't automatically guarantee that new stars will be born. The entire process of star formation is incredibly fragile and temperamental. For it to begin, a gas cloud must cool down and become dense enough for gravity to overcome the internal pressure. Many factors can interfere with this necessary collapse. One of the main enemies of star formation is something we call stellar feedback. When the first massive stars are born in a galaxy, they immediately begin to violently affect their environment. Through their powerful radiation and stellar winds, they heat up and scatter the surrounding gas. And when they finally explode as supernovae at the end of their short lives, the resulting shockwave can completely strip entire regions of the galaxy of their gas. This creates a paradoxical situation. Star formation itself creates the very conditions that inhibit further star formation. This mechanism of self-regulation should lead to a gradual decline in activity. But perhaps we have underestimated its true power. Another critically important factor is the role played by supermassive black holes. Today we know they reside at the center of virtually every major galaxy. The mass of such a black hole is directly tied to the mass of the galaxy's central bulge. This suggests that the growth of the black hole and the growth of the galaxy are two interconnected processes. When a black hole actively consumes gas, it transforms into a quasar, one of the brightest objects in the entire universe. The energy released by a quasar is colossal. It's powerful enough not just to heat the gas within the galaxy, but to entirely eject it into intergalactic space. This process is known as active galactic nucleus, or AGN, feedback. If a rapid burst of activity occurred from these galactic nuclei in the recent past of the universe, it could explain the abrupt and global cessation of star formation. Essentially, the galaxies sterilized themselves, either exhausting or violently expelling all their building material. What we observe now are the remnants of this cosmic catastrophe, the slow dying down of aging stars with no hope of replenishment. Modern cosmology is entirely predicated on the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. This essentially means that no matter where or which way we look, we should observe roughly the same structure. There's no special center or defined edge. However, recent observations are starting to challenge this fundamental assumption. What if the universe isn't as uniform as we've assumed? And what if we happen to live in a particularly special or anomalous region? Imagine, for example, that our solar system and surrounding galaxies are situated inside a gigantic bubble of unusually low matter density. Such a bubble, or void, could have formed during the early universe due to random density fluctuations. If we are positioned near the center of such a void, our entire perception of the cosmos would be skewed. We would observe distant galaxies receding from us faster than predicted, primarily because the denser matter just outside the bubble boundary is effectively pushing us away. This mechanism could easily create the illusion of accelerated expansion, the very phenomenon that dark energy was hypothesized to explain. But how does this relate to the observed cosmic dimming? If our region has an anomalously low density, the actual number of stars and galaxies immediately surrounding us would naturally be lower than the average density across the entire universe. What we perceive as a globally dim universe might just be a local effect, simply a consequence of our unlucky geographical position within the cosmos. In essence, we're living in a cosmic small town, judging the entire world by the faint lights we see, completely missing the brilliance emanating from distant galactic megacities. This concept, known formally as the giant void hypothesis, is currently a hot topic of debate in the scientific community. To test this, researchers must create extremely precise maps detailing the distribution of galaxies across various distances and directions. If this bubble is real, we should eventually detect its boundary, the point where the density of galaxies dramatically spikes. Certain existing data, such as anomalies found in the cosmic microwave background radiation, like the cold spot, already indirectly suggest the existence of such immense structures. If this hypothesis proves correct, it would force us to fundamentally rethink not only the perceived dimming of the universe, but also our entire understanding of dark energy. It might mean that dark energy doesn't exist at all, and the true answer lies solely in the non-uniformity of our cosmic neighborhood. The discovery that the universe is dimming fundamentally changes our understanding of its ultimate fate. For decades, cosmologists focused on two main possibilities. The first is the Big Crunch, Bitsune. If the average density of matter is high enough, gravity will eventually halt the expansion and reverse it. Galaxies would rush back together, temperatures would soar, and ultimately the entire cosmos would collapse into a single, superdense point, much like the one from which it began. The second is heat death. If the density of matter isn't sufficient to stop the expansion, it will continue indefinitely. Galaxies will drift apart, stars will burn out, matter will decay, and the universe will become a cold, dark, and empty void where literally nothing happens. The discovery of dark energy and the accelerating expansion of the universe made the heat death scenario far more likely. However, it also introduced a third, more exotic possibility, the Big Rip, caused by a hypothetical form of phantom dark energy. So how does this new discovery change the picture? If the dimming is caused by a sharp decline in star formation, it drastically accelerates the onset of heat death. The universe would become dark and cold much sooner than previously estimated. The stelliferous era, the age of stars, will be significantly shorter. The last stars will burn out and the cosmos will descend into perpetual darkness, inhabited only by black holes, neutron stars, and cooling white dwarfs. But if the dimming hypothesis pointing to changes in the properties of dark energy is correct, things become far more interesting. If its density continues to increase, the Big Rip awaits. Conversely, if dark energy weakens and potentially changes its sign, the Big Crunch scenario suddenly becomes possible again. We might be at a pivotal moment where expansion shifts back into contraction, and if cyclical models hold true, this current dimming is merely the prelude to a new birth. Thus, answering the question, why is the universe dimming, is not just about satisfying scientific curiosity. It is the key to understanding the ultimate fate of all existence. By studying the light of distant galaxies, we are, in essence, trying to read the final chapter of the cosmic book. And for now, we do not know if that chapter promises a happy ending, a tragic finale, or if it will simply fade out with an ellipsis, implying a new, unwritten story yet to come. Let's take a look at the cosmic dust hypothesis, but approach it from a different angle. We've already discussed how an uneven distribution of dust doesn't quite account for the global effect we're observing. But what if the change isn't in the quantity of dust, but in its properties? The chemical makeup of cosmic dust is far from static. The composition depends on which types of stars dominated during a particular epoch. Young, massive stars forge elements heavier than helium, which are then ejected into space during supernova explosions. These elements, such as carbon, oxygen, and silicon, serve as the building blocks for dust grains. Older, less massive stars, like our own Sun, also enrich the interstellar medium by shedding their outer envelopes at the end of their lives, but they contribute a different set of elements. Perhaps there has been a shift in the dominant type of dust producer relatively recently in the universe's history. For instance, the era of truly massive stars may have subsided, with aging, intermediate mass stars now providing the main contribution. This shift could alter the average size, shape, and chemical composition of the dust grains, and these specific parameters directly determine how the dust interacts with starlight. For example, larger graphite particles might absorb light across a wider range of wavelengths far more effectively than small silicate grains. If, for some reason, the process of small dust grains clumping into larger agglomerates has begun across the universe, this would lead to an increased overall extinction or opacity of intergalactic space, even if the total mass of the dust remained constant. This is a subtle and extremely complex effect, and it's notoriously difficult to verify through direct observation. It would require us to somehow determine the properties of dust in galaxies located billions of light-years away. However, there are existing techniques. For example, analyzing the polarization of light that has passed through these dust clouds can provide crucial information about the dust grains' shape and orientation. Future, more powerful telescopes may finally be able to perform these measurements and test this elegant and subtle hypothesis. It brings us back to the central idea that the universe is a complex, evolving system where everything is interconnected. From the nuclear reactions deep within stars to the microphysics of dust grains that are only fractions of a micron in size, let's revisit the idea that we inhabit a unique corner of the cosmos, but approach it from a different perspective. Instead of being situated in a cosmic void or bubble, what if we are actually located in an overdense region, say a filament or wall of the large-scale structure? On the largest scales, the universe truly resembles a massive spiderweb. Galaxies and galaxy clusters form long, thread-like structures, filaments, which cross paths at incredibly dense nodes. In between these structures lie the vast empty regions known as voids. We already know that our own galaxy, the Milky Way, is part of the local group, which belongs to the Virgo supercluster, which is, in turn, nested within the even more massive Laniakea supercluster. Clearly, we are definitely not living in the emptiest patch of the cosmos. How might this location influence our observations? Light traveling toward us from distant galaxies must pass through these dense structures. The collective gravity of galaxy clusters and filaments can act like a gigantic lens, warping and magnifying the light from objects far away. This is the effect we call gravitational lensing. We constantly observe this phenomenon and utilize it to study the distant universe. But what if we are profoundly underestimating the influence of this cosmic web on the overall observed brightness of the distant sky? It's possible that our local, overdense environment is effectively focusing light from far-off parts of the universe directly toward us, making the distant cosmos appear artificially brighter than it truly is. And maybe the observed dimming isn't a universal process at all, but a local consequence. Perhaps we, along with our entire Laniakea supercluster, are gradually moving out of an especially dense section of a filament and into a more sparsely populated area. Our cosmic lens would then become weaker and we would start seeing the universe as it really is, much dimmer. This hypothesis directly challenges the cosmological principle, suggesting that what we observe locally might not be truly representative of the universe as a whole. To test this idea, we would need to create even more precise and detailed three-dimensional maps showing the distribution of matter within hundreds of millions of light-years from us. We must pinpoint exactly how our supercluster is moving relative to this massive structure. This work is already ongoing, and its findings could fundamentally change how we interpret data regarding the universe's brightness. Perhaps darkness isn't truly encroaching. Maybe we're just exiting the spotlight. Beyond the established theories, there are even more exotic hypotheses attempting to crack the mystery of the dimming universe. These ideas operate at the very edge of modern theoretical physics and often verge on science fiction. But who knows, the ultimate truth might be hidden within one of them. One such idea revolves around the very nature of the vacuum itself. In quantum physics, the vacuum isn't an absolute void. It is, instead, filled with constantly popping in and popping out pairs of virtual particles and antiparticles. This quantum foam, or quantum soup, possesses inherent energy, which many physicists identify as the elusive dark energy. The standard model assumes that the properties of the vacuum are fixed and unchanging. But what if the vacuum can exist in different states, much like water exists as ice, liquid, or steam? Perhaps our universe currently resides in a state known as a false vacuum. This is a metastable state. It can persist for an extremely long time, but it isn't permanent. At some point, triggered by a random quantum fluctuation in a single point in space, a phase transition could occur. The vacuum would tunnel or slump into a lower, more stable energy level, the state of true vacuum. This transition would propagate at the speed of light, with a bubble of the new vacuum expanding and consuming everything in its path. Inside this bubble, the laws of physics would be completely different, and the matter we know simply couldn't survive. It's possible that the dimming we observe is an early precursor to such a phase transition. Not the transition itself, which we definitely wouldn't survive, but rather a subtle change in the properties of our false vacuum, making it less stable and impacting the way light travels. This is arguably the most terrifying of all hypotheses, as it suggests our entire universe could cease to exist without any warning whatsoever at any moment. Another wildly exotic idea relates to the so-called holographic universe. This theory suggests that our entire three-dimensional space is merely a hologram, a projection of information encoded on a two-dimensional surface at the boundary of the universe. If this is true, then both the laws of physics and space-time itself might not be fundamental, but emergent, arising from simpler underlying rules that govern this boundary information. It's possible that a subtle shift in these core rules is what leads to the macroscopic effects we observe, such as the apparent dimming of the cosmos. Regardless of which hypothesis ultimately proves correct, the puzzle of cosmic dimming has already profoundly shaped the planning of future astronomical missions and experiments. It has established a clear new trajectory for research over the coming decades, primarily focused on the construction of next-generation ground and space-based telescopes. On Earth, giant observatories are already underway, including the Extremely Large Telescope, or ELT, in Chile, and the 30-meter telescope TMT in Hawaii. With massive primary mirrors, 39 and 30 meters in diameter, respectively, these instruments will collect significantly more light than any existing telescope. This capability will allow them to study extremely faint and distant galaxies with incredible detail and analyze the composition of the intergalactic medium with unprecedented precision. In space, several missions are scheduled for launch, specifically designed to investigate dark energy and the universe's large-scale structure. These include the European Space Agency's Euclid telescope and NASA's Nancy Grace Roman Space Telescope. Their primary goal is to create three-dimensional maps charting the distribution of billions of galaxies. These maps will enable us to test the cosmological principle, pinpoint giant cosmic voids and filaments, and precisely measure how the rate of the universe's expansion has changed throughout its history. This data will serve as a crucial test for numerous theories, ranging from models involving variable dark energy to hypotheses about our own unique location in the cosmos. Furthermore, a new generation of dark matter search experiments conducted deep underground will specifically account for the possibility of dark matter decay or annihilation. Scientists will not only look for the direct collision of dark matter particles with detectors, but also for indirect signatures, the products of its decay, such as neutrinos or gamma rays. It's possible that the key to the entire mystery lies hidden within this data. Ultimately, this astronomical enigma has become a powerful driver for technological and scientific progress. It compels us to build ever more sophisticated instruments and develop increasingly intricate theories, continually pushing the boundaries of our cosmic understanding. Let's run a thought experiment. Imagine we are a super civilization living 1 trillion years in the future. What would our universe look like? Based on current scientific models, particularly the heat death scenario, the outlook is rather bleak. Due to accelerated expansion, every galaxy outside of our local group, which by then will likely have merged into one gigantic elliptical galaxy, will have flown beyond the visible horizon. The sky will be virtually empty. The last stars, the dimmest red dwarfs, will burn out, leaving behind only cooling white dwarfs, neutron stars, and black holes. The universe will be plunged into near-total darkness and cold, approaching absolute zero. This is known as the degenerate era. But even that isn't the final chapter. On vastly greater timescales, around 10 to the power of 40 years, 1040 years, protons, according to certain grand unified theories, may begin to decay. This means all baryonic matter the stuff planets and dead stars are made of will slowly evaporate, turning into radiation and leptons. The only remaining macroscopic objects in the universe will be black holes. But even black holes are not immortal. Thanks to Hawking radiation, they will very slowly evaporate, losing mass. Supermassive black holes at the centers of former galaxies will take an unimaginable length of time, on the order of 10 to the power of 100 years. 10 to 100 years. But eventually they too will dissipate. Following this, the dark era will begin. The universe will be a virtually empty vacuum, populated only by relic photons, neutrinos, and perhaps stable particles like electrons and positrons. All organized structure will vanish. Time itself will lose all meaning. The slow dimming of the universe that we observe today is the very first, barely perceptible step on this long journey into oblivion. It is the initial reminder that even the cosmos has a history, complete with a beginning and an end. We are living in its brightest and most energetic period, and we should appreciate every photon of light reaching us from distant stars, because someday that light will be extinguished forever. To truly grasp the problem of the universe dimming, we must first distinguish between the light we actually observe and the total energy output generated by the cosmos. These two things are not always the same. Most of the energy produced during star formation is initially emitted in the ultraviolet range, by young, hot stars. However, that UV light often doesn't reach us directly. Instead, it gets absorbed by clouds of dust within the host galaxies. This dust heats up and re-emits that energy, primarily in the far infrared spectrum. Therefore, achieving a complete picture of the universe's energy budget requires observing it across all wavelengths, from gamma rays down to radio waves. This is precisely what the Gamma project and subsequent research set out to do. Scientists compiled data from dozens of different telescopes, each operating in its specific range. They effectively conducted a complete accounting audit of cosmic energy. The conclusion was unambiguous. The decline is specifically in the total energy generation. This isn't just an effect of light struggling to reach us or simply shifting into another range. The issue lies squarely with the power station. The generators themselves, the stars, are either working less efficiently or there are fewer of them. This is a crucial distinction that helps rule out several other hypotheses. For instance, if the only factor was a change in dust properties, we would observe UV brightness declining while infrared brightness increased because more energy would be re-emitted by the dust. But observations show a decline across all wavelengths, although at varying rates. This confirms that the root of the problem lies in the fundamental process fueling the universe, the nuclear fusion occurring within the hearts of stars. This understanding significantly narrows the scope of our search and compels us to focus on questions like, why are stars forming less frequently? Or why are newer generations of stars, on average, less massive and therefore less luminous than their predecessors? The answer likely lies hidden within the complex ecosystem of galaxies, where gravity, gas hydrodynamics, and feedback from stars and black holes are all intricately intertwined. Let's delve deeper into the role of dark energy, as this is one of the most intriguing and far-reaching hypotheses in cosmology. We usually think of it as a constant force, uniformly spread throughout all of space. However, theoretical physics offers numerous models where dark energy is a dynamic field, much like the electromagnetic or gravitational fields. This type of field is known as quintessence. Unlike the cosmological constant, the energy density of such a field can change over time and vary across space. It might slowly roll towards its minimum energy state, similar to a ball moving across a hilly landscape. Depending on the topography of this energy landscape, its behavior can be highly variable. It could trigger periods of accelerated expansion, which are then followed by periods of deceleration. How might this lead to the dimming effect? Imagine that our quintessence field not only dictates the rate of the universe's expansion, but also weakly interacts with ordinary matter. For instance, it might influence the efficiency of gravitational collapse in gas clouds. If the field recently transitioned into a new state, this shift could simultaneously change the rules of the game for star formation across the entire universe. Perhaps it increased the effective pressure within the gas, preventing it from collapsing efficiently. This idea is highly appealing to theorists because it potentially allows us to solve several cosmological puzzles in one fell swoop. Take, for example, the cosmic coincidence problem. Why is the energy density of dark energy roughly the same order of magnitude as the density of matter in the current epoch? If these two components interact, this might not be a random coincidence, but rather the inevitable result of their co-evolution. Of course, these are currently just hypotheses. We have no direct proof that the quintessence field exists, let alone that it interacts with matter. Yet these models demonstrate how closely interwoven the most fundamental questions of physics can be. The mystery of the dimmed galaxies could actually be a window into a completely new sector of reality we never even suspected existed. Studying this phenomenon might lead us to understand the true nature of the mysterious force governing the fate of our universe. To understand why star formation is slowing down, we need to bring up another key factor, the chemical evolution of the universe. The very first stars were made almost entirely of hydrogen and helium, the elements forged in the Big Bang. It was inside these stars and during their explosive deaths that heavier elements were created. Astronomers collectively call these heavier elements metals. Each successive generation of stars was slightly richer in these metals than the last, a process known as chemical enrichment. So how does this relate to the birth of new stars? Metals play a crucial role in cooling down massive gas clouds. Atoms of these heavy elements are incredibly effective at radiating thermal energy, allowing the cloud to cool quickly, contract, and then fragment into individual stars. In gas that is metal-poor, this cooling process is far less efficient. Paradoxically, the more metals present in the gas, the easier it is for stars to form, especially low-mass ones. However, there's a flip side to this. Higher metallicity also leads to the formation of more cosmic dust, and dust, as we know, can block light and hinder the further cooling of the densest core regions of those clouds. Furthermore, a star's chemical composition directly impacts its life cycle. Stars that are metal-rich have more opaque outer layers, which fundamentally alters their structure and evolution. They tend to live slightly longer and exhibit stronger stellar winds. It is possible that the observed darkening is directly linked to the universe reaching some critical level of chemical enrichment. The metallicity of the gas within galaxies may have become so high that it fundamentally changed the star formation regime. Perhaps this means the universe is now producing mainly less massive and therefore less luminous stars. Alternatively, maybe the increased amount of dust is now more effectively suppressing star birth in the most active regions. This is a complex, multi-factor problem. The ultimate outcome depends on a delicate balance between cooling, heating, gravity, and stellar feedback. To untangle this, scientists are constructing sophisticated computer models that simulate the evolution of entire galaxies over billions of years. By comparing the results of these simulations with real-world observations, they are trying to pinpoint the critical parameter that shifted in the relatively recent past, leading to the effect we see today. Let's talk about scale. When we say half the universe has gone darker, it sounds dramatic, like someone flipped a giant light switch. In reality, we're talking about an incredibly subtle effect, one that you can only spot when analyzing colossal amounts of data. The annual change in luminosity is just a fraction of a percent, but over billions of years, this effect accumulates and becomes quite substantial. A good analogy for this is human aging. We change imperceptibly day by day, but if you compare a photograph of someone at age 20 versus 60, the difference is obvious. The universe behaves the same way. We observe it at different ages by looking at galaxies at varying distances. We see that the 60-year-old universe, meaning the galaxies closer to us, is significantly dimmer than the 20-year-old universe, which is represented by those distant galaxies whose light has traveled a long time to reach us. The problem is that this aging process is happening faster than our cosmological models predicted. It's as if the universe is suffering from premature aging. Another critical aspect of scale is defining exactly which half of the universe we're referring to. Obviously, it's not a geographical division. What we mean is that the total energy emitted per unit volume of space has halved over the last 2 billion years. In some areas, active galaxies with intense star formation, the light is still blazing brightly. In others, namely old, dead, elliptical galaxies, that light went out a long time ago. The observed effect tells us that the balance has shifted towards the latter. The processes that lead to the death of galaxies have begun to dominate over the mechanisms that sustain their life. Understanding this scale is crucial so we don't panic. Our sun will shine for another 5 billion years, and this phenomenon will not affect human life in the foreseeable future. However, for science, for our understanding of the fundamental laws of the cosmos, this discovery is tremendously important. It's like a doctor studying aging suddenly finding that every human on the planet began aging twice as fast. That discovery would force them to completely overhaul their understanding of biology. One of the most reliable methods for testing whether dark energy's properties change over time is by examining what we call baryon acoustic oscillations, or BAO. What are they exactly? In the early universe, which was a hot, dense plasma of particles and radiation, sound waves spread out like ripples after a stone hits the water. These waves cause small but important density fluctuations in the matter. When the universe finally cooled and became transparent, these waves essentially froze in place. They left a characteristic imprint on the distribution of matter, a kind of standard cosmic ruler. we observe that galaxies tend to cluster at a specific separation distance, which corresponds precisely to the distance these sound waves traveled before freezing. This scale is roughly 500 million light-years. Because we know the actual intrinsic size of this ruler, we can use it to measure distances across the cosmos and, crucially, map the history of its expansion. By measuring the apparent angular size of this fixed ruler across different epochs, different distances in time, we can reconstruct the expansion rate with high precision. This method is completely independent of standard candles like supernovae, making it an incredibly powerful, standalone tool. Projects such as the Sloan Digital Sky Survey, or SDSS, and the Dark Energy Spectroscopic Instrument, DESI, have already mapped the positions of millions of galaxies and quasars to chart these oscillations. If dark energy is not a static cosmological constant but varies over cosmic time, the BAO data should reveal it. We would observe deviations in the expansion history compared to the predictions of the standard model. So far, the measurements are highly consistent with the standard cosmological model, which treats dark energy as a constant. However, the precision of these measurements is constantly improving. Upcoming surveys, which will map tens of millions of galaxies, will allow us to test this hypothesis with even greater rigor. If they find deviations, it will trigger a genuine revolution in physics. If they don't, then we'll have to look for explanations for the universe's accelerating expansion in other, potentially more complex astrophysical processes. Either way, the BAO cosmic ruler remains one of our biggest advantages in this scientific pursuit. Let's turn once more to the hypothesis that our physical laws might be incomplete. One of the biggest challenges in modern theoretical physics is the so-called fine-tuning problem. Many fundamental constants, such as the electron's mass, the gravitational constant, or the value of the cosmological constant, have values that seem impossibly precise, perfectly tailored for the existence of a complex universe and life. If these values were even slightly different, stars couldn't burn, heavy elements wouldn't form, and the universe would either instantly collapse or expand so quickly that matter couldn't coalesce into galaxies. There are several philosophical and scientific approaches to addressing this issue. One is the anthropic principle, which suggests we observe this specific universe only because we couldn't exist in any other kind. Another approach is the multiverse theory, which posits countless universes governed by different physical laws, and we simply reside in one of the successful ones. But there is also a third path. Perhaps these constants aren't truly constant after all. They might be slowly changing, evolving alongside the universe itself. If this is the case, the cosmic dimming we've observed could be a direct consequence of this evolution. For example, a minor shift in the fine structure constant, which governs the strength of the electromagnetic interaction, could drastically alter nuclear reactions in stars, making them significantly less efficient. Similarly, a change in the gravitational constant might influence the conditions required for gas clouds to collapse and form stars. The search for possible shifts in fundamental constants has been underway for decades. Scientists analyze the spectra of distant quasars, looking for evidence that atomic transitions in the past occurred using slightly different constant values. The results of these initial searches remain highly contradictory and push the very limits of our detection methods. However, if it is ever proven that even a single fundamental constant changes over time, it would represent a discovery comparable in significance to the theory of relativity, and the mystery of the dimming universe may yet provide some of the first observational evidence supporting this thrilling new worldview. It's fascinating to look at the darkening of the universe through the lens of information theory. Some theories suggest that information is just as fundamental a component of reality as energy and matter. The universe itself essentially acts as a gigantic quantum computer, constantly processing data. What does information mean in this context? It fundamentally represents the degree of order or complexity within a system, the birth of a star, the formation of a planetary system, the emergence of life. All these processes create complex, ordered structures, thereby increasing the total amount of information. Conversely, the second law of thermodynamics states that entropy, or the measure of chaos, in a closed system always tends towards a maximum. This means that over time, any ordered structure must inevitably break down, and information must be lost. These two processes, the creation of information known as negentropy and its destruction known as entropy, are locked in a constant struggle. Perhaps the era of active star formation was the period when information creation dominated the universe. Gravity actively pulled scattered matter into complex structures, forming stars and galaxies. But now, as the fuel reserves for these processes dwindle, the second law of thermodynamics is starting to gain the upper hand. Entropy is asserting itself. The darkening we observe isn't just a reduction in energy output. It could be a powerful sign that the universe is transitioning from a phase of creation to one of decay. The speed of information processing is slowing down and complex structures are beginning to degrade. Granted, this is a highly philosophical perspective, one that is difficult to formalize into strict mathematical equations. However, it allows us to view this problem in a much broader context. The darkening of the universe is not merely an astrophysical phenomenon. It may be the manifestation of nature's most fundamental law, the relentless march of time from order toward chaos. And we are witnesses to the very moment when this great pendulum swings back. In any scientific study, especially when dealing with such subtle effects, there's always the possibility that we might be falling victim to cognitive biases or systematic errors. The history of astronomy is full of examples where groundbreaking discoveries turned out to be mere artifacts. Just recall the famous canals on Mars, which were revealed to be an optical illusion, or the discovery of faster-than-light neutrinos, which was ultimately traced back to a loose cable. Can we be sure that the dimming of the universe is a genuine effect and not something similar? Scientists are taking this possibility extremely seriously. This is exactly why so much time and effort is spent cross-checking data obtained from different instruments using various methods. Data from the Gamma project was compared with observations from the Sloan Digital Sky Survey, as well as space telescopes like Hubble, Spitzer, Herschel, and many others. And overall, they all point toward the same trend. This significantly reduces the likelihood that the problem lies within a single instrument. A more complicated issue involves the analysis methodologies themselves. To measure total luminosity, researchers must make numerous assumptions and rely on various models. For instance, how do we correctly account for light absorption within the galaxies themselves? How do we reliably extrapolate data gathered from a limited patch of sky to represent the entire universe? How do we accurately translate the observed brightness across various filters into the total energy output? In each of these procedures, a small systematic error could be hiding, which, when accumulated, might lead to a false result. This is precisely why there is such a vigorous discussion happening within the scientific community. Different teams are analyzing the exact same data, using slightly different approaches and comparing their outcomes. So far, the consensus leans toward the effect being real. However, ultimate confidence will only come once we receive data from the next generation of telescopes, allowing us to take measurements with much smaller margins of error and fewer model dependencies. Science is a path of slow, careful approximation toward the truth, and along this journey, it is vital to always leave room for doubt. Imagine for a moment that the simplest hypothesis holds true. The universe is simply running out of the necessary fuel for stars. The gas supply dwindles, new stars are born ever more rarely, and the old ones slowly burn out. What does this mean for the potential existence of life down the line? On the surface, the prospects look bleak. Fewer stars equal fewer planetary systems. Fewer massive stars mean less of the heavy elements required for biochemistry. The cosmos becomes increasingly inhospitable, and yet some scientists hold a more optimistic view. They point out that the most turbulent eras of star formation may not have been the best time for life to take hold. Frequent supernova explosions and intense radiation from young stars could easily sterilize nascent planets. A calmer, more mature universe might actually be a more conducive environment. The ultimate long-term challenge, however, will be the dimming of the ultra-long-lived stars, the red dwarfs. They can burn for trillions of years, vastly longer than stars like our own Sun. It is likely around these dwarfs that the last persistent pockets of life will be concentrated in the universe, but even they will eventually exhaust their fuel. Does this spell the definitive end for all things living and conscious? Not necessarily. Physicist Freeman Dyson and other visionary thinkers explored scenarios for survival far into the cosmic future. Super civilizations might learn to harness alternative power sources. For instance, they could extract rotational energy from black holes through the Penrose process. Alternatively, they might learn to exist as purely informational structures requiring minimal energy expenditure. They would adapt to the continuously cooling universe by radically slowing down their metabolism and their very thought processes. This is what Dyson termed eternal survival. Naturally, these concepts stretch far beyond the limits of current science. Yet these reflections demonstrate that even in a slowly dying, darkening universe, the narrative may still be ongoing. The eventual cooling and darkening of the cosmos is a challenge not just to our scientific comprehension, but ultimately to our survival as a species. It serves as a stark reminder: if humanity wants to secure a future on such grand scales, we will need to master the control of energy and matter at a level we currently consider nothing short of divine. Ultimately, the perplexing mystery of why the universe appears to be dimming offers a perfect demonstration of the scientific method in action. It always starts with an unexpected observation, a piece of data that simply doesn't fit the existing worldview. This observation, often uncovered by new and more sensitive instruments, directly challenges established theory. This is immediately followed by the crucial process of hypothesis generation. Scientists propose a whole spectrum of possible explanations, ranging from the most conservative adjustments to the most radical, paradigm-shifting ideas. Crucially, each of these competing hypotheses makes specific, testable predictions. For instance, the cosmic dust hypothesis predicts a measurable reddening of light, while the dark energy modification hypothesis predicts observable deviations in the universe's expansion history. The next vital stage is rigorous testing. Astronomers design new observational surveys, theorists refine their mathematical models, and engineers build groundbreaking instruments. This is a long, painstaking process, often riddled with dead ends and false leads. Some hypotheses are discarded outright because their predictions fail to materialize. Others are modified and refined to better align with the incoming data. Occasionally, solving the puzzle requires a fundamentally new, revolutionary idea, a single concept that binds fragmented facts into one coherent, elegant framework. We are currently right in the middle of this thrilling search. We have the core mystery, we have several competing hypotheses, and, crucially, we have the cutting-edge instruments required to test them all. This is an incredibly exciting era for cosmology. The answer might be discovered in the next few years, perhaps through the capabilities of the James Webb Space Telescope or the Euclid Observatory. Or perhaps this secret will remain elusive for decades, demanding even bolder theoretical insights and much more powerful technology. Regardless of the timeline, the very process of seeking the answer is already enriching our understanding of the cosmos. Every hypothesis that is tested and rejected narrows the field of possibilities, bringing us closer to the truth. And that ultimately is the core purpose and enduring beauty of science itself. And so we conclude our long and hopefully soothing journey deep into the heart of one of modern science's greatest unsolved puzzles. We've seen how the meticulous analysis of light from hundreds of thousands of galaxies led scientists to a startling realization. Our universe is growing darker, and it's happening far more rapidly than anyone anticipated. We examined a multitude of possible explanations. Perhaps cosmic dust is to blame, shrouding our view like a thick interstellar fog. Or maybe the universe is simply aging, and the era of explosive star formation is drawing to a close, giving way to a quiet, darker maturity. We peered into the deepest corners of the cosmos, speculating about the mysterious, dark energy that might be changing its properties and dictating the ultimate fate of creation itself. We even dared to suggest that our fundamental laws of physics are incomplete, and that we stand on the cusp of a whole new scientific revolution. For now, we are left without a definitive answer. Every hypothesis holds both strengths and weaknesses. The universe, as always, has proven to be far more complex and fascinating than our boldest theoretical models. But one thing is certain: we are witnessing a pivotal moment in our understanding of the cosmos. This mystery compels us to push forward, to build new telescopes, to formulate new theories, and to ask ever deeper questions. Thank you for spending this time with me, diving into this cosmic enigma. I hope this discussion has helped you relax and prepare for sleep. If you enjoyed this journey, please don't forget to subscribe and hit that like button. And before you drift completely off, I want to leave you with one final question. Which of these theories seems the most plausible to you, or perhaps simply the most beautiful? What do you think lies behind this encroaching cosmic darkness? Share your thoughts in the comments below. Good night.